As UAVs become more and more ubiquitous in our society, it is becoming increasingly important to be able to manage their interactions with the world and to be able to maximize the full potential of this technology. In this video, we will explore some of the benefits that a voxel-based UAV data management solution could provide for managing UAV traffic in a dense urban environment. We will run through a number of use cases and how our data management system can handle these situations. For this demonstration, we are using freely available mesh data of the city centre of Adelaide. We use a mesh voxelization algorithm to convert the Adelaide city centre into an array of voxels. These voxels will be used to store information about the UAVs and the environment they are interacting with. It provides an optimized and manageable system for us to store and retrieve large quantities of spatial data from. We've got a number of UAVs scattered throughout the city centre with random tasks assigned to them. When we begin the simulation, the UAVs will attempt to find a route to their desired destination and begin their flight. When a UAV arrives at its destination, it will move on to its next task and fly elsewhere. Because we can store a UAV's route in the voxels, the system does not allow UAV routes to overlap and can provide each UAV with a unique path that does not intersect with any other path. This is an efficient way to manage air traffic for many UAVs travelling to a variety of destinations. By toggling the UAV path voxels, we can see how the paths are constructed, and we can confirm that no paths intersect. As a UAV traverses its path, it frees up the voxels behind it so that the other UAVs can travel through that space if they need to. In this simulation, we're able to select one or more UAVs, which will provide us with a camera feed showing the selected UAV's point of view. With a UAV selected, we can interrupt its tasks and tell it to go directly to a destination. The system will find a route for it to take and it will fly to its new destination. The system has support for swarm behaviour, so it is also possible to select multiple UAVs and tell them to go to specific destinations. A lead UAV will be provided with a route to take to the destination, and the other UAVs will use swarm behaviour while avoiding collisions with other UAVs and obstacles such as buildings. An interesting use case to consider is to use UAVs as a courier service to deliver packages. We are able to simulate this capability in our system by placing virtual packages in the environment and giving them delivery instructions. Now that we've placed a package, we can tell one of our UAVs to scan it, pick it up and deliver it to its destination. Another potential use case for using UAVs in an urban environment is to search for something. In this example, we can tell a UAV to look for hazards or dangerous objects. We can visualize what the UAV can see by painting the blocks within its vicinity. This shows us where the UAV has already searched and what areas are still unknown to it. If we place, for example, a bomb, the UAV will conduct a search for this type of object until it finds it, or until it has covered this block of the city. It's also possible for us to paint directly onto the voxels. This painted data could be used to designate areas of interest for UAVs to inspect, which could be useful for disaster surveying or to inspect a building for maintenance reasons. An important aspect of UAV traffic management is to ensure UAVs can't fly where they're not supposed to, whether that be densely populated areas, zones with restricted clearance, or zones that may contain flight paths of larger aircraft. We can show this in the simulation by using geofences, which are virtual restricted zones that UAVs are not allowed to travel through.